Hello everybody, I'm here with an example of again acceleration described in NT-coordinate system. This is actually a problem which combines kind of the projectile motion equations with NT-coordinate system, and I want to show you actually two ways to solve this problem. So here we have this water or whatever fluid leaving the nozzle here at velocity of velocity of 60 feet per second at A, and it's coming out of the nozzle horizontally, and then it's going to hit the wall 120 feet away horizontally at point B. So the question is, if we are given the initial velocity which is coming out of the nozzle horizontally at 60 feet per second, what would be the radius of curvature at point B? So as I said, I want to show you two ways to do this problem. One would be based on the fact that normal acceleration at any instant is v squared over rho. So if we rearrange the equation, rho can be determined by dividing v squared by a sub n. So if you could go ahead and find velocity at b, right? And I'm going to show you how you can do that. And then also if you could figure out what an is, then we are all set. We just plug into this equation. Okay? So how do we go about doing that? So let's start with the projectile motion equations. You guys remember that the first thing you want to do is to take any initial velocity and break it into two components, x and y components. In this case, v0x is actually 60 feet per second because the angle in a way is zero, is coming out horizontally, and there is no y component of velocity, so v0y is zero. Now you guys remember, in order to find velocity you need the x component and the y component of velocity at any instant. The x component never changes because we are neglecting the air resistance, so that's v0x, so that would be 60 feet per second. The y component changes according to this equation, v0y minus gt. So the question is, we already know Vx is 60, but what about Vy? How long does it take for the water to get from A to B? That's the one what we have to determine. And that could be determined easily. You guys remember that since we are given the horizontal position between point A and B, or the horizontal distance between point A and B, we could use this equation. X being 120, if we pick our reference right here at A, and x0 is 0 and v0x is 60. So actually, clearly, it takes 2 seconds for the water or the fluid to get from point A to B. So now I can go ahead and find v sub y at point B. So that would be v0y, which is 0, minus gt. So this is 0, right? And g is 32.2 times 2 seconds. So the speed is 64.4 negative, which makes sense. So actually velocity at B, remember the x component is 60 feet per second, that never changes. So 60 in the x and 64.4, a little bit more than 60 in the y. So velocity of V, velocity at B actually would be something like that, which becomes square root of 60 squared and negative 60.4 squared, which is about, I believe, 88 feet per second, a little bit more than 88. We'll just round it to 88 feet per second. So we are halfway done. We already got velocity of B. Here we go. So now the question is, how do we find this normal acceleration, guys? How do we find that normal acceleration? That normal acceleration always is determined based on this angle, guys. You see, what determines the tangential axis is always velocity. Remember, velocity is always along the tangential axis. Remember, velocity has to be tangent to the path. So you see, this is the tangential axis always, tangent to the path. So you see, if I go ahead and find that angle, it's easy to find that angle. Tangent of that angle is opposite over adjacent. So if you do the calculation, theta comes out to be a little bit more than 45 degrees, 47 degrees. Okay, roughly, a little bit more than 47 actually. All right, how are we going to find this angle to find normal acceleration? Let me move to the next page. So let me draw this point B. So remember, this is the tangential axis. This is the normal axis at that instant, right? And remember, this angle theta was the 47 degrees that we determined, right? And the question is, what is the, let me get rid of that and make it nicer. What is the total acceleration, guys, for projectile motion? Once the water leaves the nozzle here, what controls is gravity. So the total acceleration in these type of problems is always gravity, in this case 32.2 pointing down, feet per second squared. So if I take the gravity, which is the total acceleration, right? How much of that is along the normal axis? See, this is, if you break it, if you project it along normal and tangential, this would be the normal component, and this would be the tangential component. So I need the normal component. Remember, if this is theta, this would be also theta. So clearly, A sub n in this picture, you could see A sub n is A, which is 32.2, or G, times cosine theta. And remember, theta we already determined to be 47 degrees. So AN happens to be about, I believe, let me just calculate that for you. It looks like I haven't calculated that. So 32.2 times cosine 47, sorry for the delay. It's about 21.96 feet per second squared, guys. And now I can go ahead and, remember in the equation over here, rho sub B was what? V squared divided by AN. That's velocity at B squared divided by AN. Velocity was 88 feet per second, roughly, squared, divided by this number that I just got for you. So rho at B comes out to be about 352.63. So remember, we did a lot of rounding off to get this number. Now, I want to show you a different way, totally different way. A way based on this equation, guys. You've seen this equation before. What if we were able to find the profile of the path, the equation of the path of motion, the equation that the water follows along the curved path? Then we should be able to use this formula to find rho. And let's see how close we come to the value that we got based on this other approach. Of course, if you don't round off, you should get exactly the same answer. All right, so I have to move to the next page to show you what's going on. So look, guys, my objective is, so this is point A where the water leaves the nozzle, and it's going to take a path like this, right? And this is point B, right? If I find the equation, so let me say this is my x-axis, right? This is the x-axis, and this is the y-axis. And let me just erase this. Put A back here, okay? So, what would be the equation of this path, y as a function of x? It's always, guys, based on the two equations of the projectile. X equal x0 plus v0 xt. Of course, our x0 is 0 because we are at the reference at point A. So x equal v0x, remember, is the water leaving the nozzle, 60t. Don't plug in the x of 120 here. Just leave it alone. The other equation, y equal y0 plus v0 yt minus 1/2 gt squared. So y0 is 0, v0y is also 0, makes things easier for us. So y equal negative 1/2 32.2 t squared. So this becomes minus 16.1 t squared. So it always comes down to do a very simple substitution, guys. If you could say, if you could have t in terms of x, t is equal to what? X over 60. And you take this and you plug it in here in place of t. So look, let's see what happens. Let me actually switch to back to black. So y equal minus 16.1. But what is t? T is x over 60 squared. So if you clean this up, this comes out to be, I have written it down here for you, comes out to be minus 0.00447 x squared. Very small number here as the coefficient of x squared. So now we are ready to apply the equation. Remember the equation from the previous page? Anytime you have, so basically this is the equation of this parabola, guys. All right, y equal f a function of x. So here we go. By the way, what x do we plug in here? Where do we trying to find the radius of curvature at B? What is x at B? X is 120 that is given. So we're going to plug in the 120 feet here. All right, very simple, guys. So now taking the derivative is easy, no problem. So we need y prime, which actually becomes negative 0.008, I believe 944x, and y double prime actually just becomes minus 0.008944. Plug in x equal 120 here, right, before you actually put it into the formula. This comes out to be about negative 1.0733. Remember, guys, we're doing a lot of rounding off here. All right, so we're ready. And by the way, y double prime doesn't have even any x to plug in. So we have 1 plus y prime squared, which is what? Negative 1.0733 squared. The whole thing then, guys, be careful, raised to power 3 halves, divided by the absolute value of minus 0.0088944. So remember, rho has to come out to be positive. I think if you do the calculation, you get 352.97 based on these numbers that I have here. And look, that's very close to what I had before, guys. Let's go back. What rho did I get? Why there is a discrepancy? Because of all the rounding off that we did. We did rounding off here. We did rounding off in the angle, 47 degrees. We did rounding off, almost in everything, even in the 88 here. All right. So, so you saw two methods. One based on normal acceleration being v squared over rho, and the other approach is based on the profile of the path, where you can use this very useful equation to find the radius of curvature. Again, as always, thanks for watching and listening. And if you are liking these videos, you can subscribe, and I will have many of these videos coming your way as we continue with the topic of dynamics. We move to the kinetics of particles, talking about work energy, impulse momentum. Then we get to kinematics of rigid bodies and kinetics of rigid bodies. Thanks.